Let me give back your tests. First, I'm coming with a test key, and I will uh, post it online as well. Then let me hand your test back. Because some of this was a little messier than I meant for it to be, uh, I added like 6 points on here. And yeah, the key is missing the graph on the slope field, but everybody got that pretty much right, so I didn't need to worry about that. A few things just to remember is just basic differentiation stuff, product rule. Use that. There were some places there where people didn't use product rule. Also, make sure you got implicit differentiation, because if you're showing something like number 2 is an implicit solution, the idea is don't try to solve for y. So make sure you can do implicit differentiation, that knew your basic derivative stuff that you're okay with. What turned out to be messier than what I meant, what I kind of wanted, was like number 5. I've used these problems before, but on those I basically just asked people to just say yes or no to each one. Whereas on this one I said, well, let's just take home. I'll ask people to start verifying this. Give me some reason. Don't just say it's Bernoulli. Show me why. And that turned out, some of these were kind of long to actually, if you're going to go through all of that. Just for reference here, if something is linear, it's automatically Bernoulli, because Bernoulli, the only difference between that and a linear one is the Bernoulli has, on the right hand side, it has a function of x times the power of y. And if that power was 0, then it would be linear. So linears are automatically Bernoulli. Problem number C is Bernoulli without being linear. And some of these I have, even though 5b is exact, I have no idea how much trouble it'd be to solve, actually. Same thing about C. It's a separable equation, but I really don't want to try to do that. No. Okay, and let's see, what else to say? I don't know that there's a whole lot else to say on here. Yeah, a little bit. Appear to be unlined. I want to take a look at number 6C. This isn't hard, but I don't do it exactly like the book does. And I actually kind of like my way a little better. I think on some of the examples I did it the same way the book did. But this was 5x plus 4y dx, 4x minus 8y cubed dy. Okay, and this is exact because this is m here and this is n. The partial of m with respect to y is 4, and that's the partial of n with respect to x. Okay. All right, so for an exact DE, they're really straightforward to solve. Is you go to the m function and integrate with respect to x. And you're going to get 5 halves x squared, 4xy or 4yx, plus some function of y. Now, the book had us do something else. Take the partial of this with respect to y and then integrate. I don't really see why to do that. Go to n, take the partial of n with respect to y. I mean, to integrate that, because that's what it was. This is the partial of whatever our big function was with respect to y. So integrate this with respect to y, 4x minus 8y cubed dy. So you get a 4xy, a minus 2y to the fourth. I'm in a hurry and I get extra sloppy. 4xy minus 2y to the fourth, plus there's some unknown function of x. This guy is your unknown function of x, and this guy here is your unknown function of y. So you have your 5/2 x squared. That didn't show up when we found n. We've got 4xy, which is common to both of them. And then we have a minus 2y squared. That's the y term that didn't show up on the first one. So I think that's actually makes a little more sense than the way they have you do it in the text. Integrate both of them, and whatever's missed, they have a term in common, so just write that down once. But the x term you get from the first is the x constant you would get when you integrate it in. The y term that you get in the second one is the y constant that you get when you integrate in. And I think that's just a little bit better than what they do. Okay. Let's see. Not a whole lot else to say on that one that I can think of. Let me look at my key and see if there's anything I want to point out. No. Okay. Well, there's that. And I need to rearrange some things here. Okay. Hey, have any questions about anything? Okay, so here's where we were. We're going to back up a little bit and kind of put things in perspective, but we're in the process of trying to solve something like equation 1 here, which is a linear second order differential equation with constant coefficients. And what we saw last time was where it comes up, and it comes up, among other things, in the spring mass damper system. We'll also see linear second order constant coefficient equations when we do electrical circuits as well. Okay. Now, in order to solve this, we first figure out how to solve the homogeneous form, which does not have this function over here at the right. So we're just looking at the dE without some sometimes called a forcing function of t here. That's called a homogeneous form, all right? And I looked at my notes. And actually, I looked at my notes first, but we'll come back to. I'll have to stick an extra page in here and do something here. The homogeneous form, because the solutions to solve this first equation, we're going to first solve the homogeneous form, and then worry about how this forcing function affects the solution to the homogeneous form. And to solve the homogeneous form is we form an auxiliary equation, and the reason this works is I kind of went through it last time. You looking at what this homogeneous equation looks like, it's just some linear combination, just constants times a variable, a function y and its derivatives. And a typical function so in other words, the function y and its first derivative and its second derivative ought to all look about the same. And the types of functions that do that are basically exponential functions. And I showed, well, if e to the rt was a solution of that, it could be a solution to that if this auxiliary equation is 0. And the auxiliary equation is basically just take the coefficients of the homogeneous one, replace the y double prime with a variable generally called r squared, y prime with r, and c is just the constant there. And we've been in the process of looking at the auxiliary equation because solutions to this will generate solutions to equation number 2 above. Okay, now what I'm going to do now is kind of pause and insert something that I should have done before this slide. But we'll come back to this slide. We did several things the other day, and I wanted to. We talked about what it meant for. Let me back up here. We talked about what it meant for one of these guys to have actually a homogeneous equation to have a solution. And the nice thing about it is they have solutions pretty much everywhere. So it's not like we have to worry about some of the regions in the plane like we did on some of the stuff in Chapter 1. And generally, since this is a second order DE here, we're going to have basically more than one solution that we'll put together. And that's where we need to talk about linearly independent solutions. So we have this. We had if y1 and y2 are linearly independent, solutions to that equation, to the homogeneous form, then the general solution is y equals some constant times y1. Of course, these are functions of t, plus some other constant times y2. C1 and C2 are constants. Okay, now we had a definition for linearly independent. Two linearly independent solutions is basically one is not a multiple of the other. Well, that's wonderful. Okay, one is not a constant multiple of the other. That's pretty easy to tell if you've got two, but if that's not the definition when you've got 3 or 4 or more solutions. So I'm going to give you something. This is basically an idea I'm not going to prove work problem number 34, but this is basically an idea that's mentioned in problem 34 on page, in section 4.2. Yes, this is on page 164. And I want to do this because the idea that they introduced in number 34 can be expanded to handle 3, 4, or more functions, and that's what we're going to do. Right now, we're just working with second order DEs, so we're only going to get 2 possible solutions. If we're working with higher order ones, we get more possible solutions. Okay, so it's a definition. Besides, I like the definition here. For 2 differentiable functions, y1 and y2. So these are both functions of t or whatever. Okay. The Wronskian, W-R-O-N-S-K-I-A-N. The Wronskian is defined to be W of y1 comma y2. And this book used brackets. It is a determinant. Y1, Y2 in the first row, Y1 prime, Y2 prime. Now you don't have to know what determinants are if you haven't had linear algebra. I know a couple of you had. It's so it's like Y1 times Y2 prime minus Y1 prime times Y2. So it's a kind of a cross product sort of thing here. Okay, and the reason we're doing this is two differentiable functions are linearly independent if their Wronskian is not equal to 0. Okay, now Wronskian comes from a Polish mathematician. Can't remember his first name, but Wronskian. Okay, so this gives us a quick way of checking if two differentiable functions are linearly. We just take this Wronskian and look at it. If it's equal to 0 anywhere, then they're not equal to 0. This should be actually an if and only if here. Then they're linearly independent. And this expands. I'll the next, yeah, we'll do an example here. But if I had three functions, then I'd have, and I'll write it down what the matrix looks, the determinant looks like for three functions. But it's a nice little check to see if things are linearly independent, just involving derivatives. Okay, well, let's do an example here. I want to do number 20, back up and do number 29. Now, the problem number 29, they didn't want us to use this, or they wanted us to go with the basic definition. But let's change the I just like that term, Wronskian. Use the Wronskian to show that y1 equal t e to the 2t, y2 equal just e to the 2t are linearly independent. So maybe you can look at that and tell that one of those is not a constant multiple of the other. Well, we're going to do it with the Wronskian. So wait till we get kind of caught up here, then I'll go on to the next, to a new board. It's getting kind of full. There shouldn't be any 7s in here. Everything should be 2s, 1s and 2s. And my handwriting's bad, but it's even worse on white on the smartboard. So we need to take derivatives of these guys, and then we're going to plug them into that determinant and simplify it. So y1 is t e to the 2t. So what's the derivative of that? Product rule. First times the second, the first times the second. So 1 times e to the 2t plus the first times the derivative of the second. So y prime is e to the 2t plus 2t e to the 2t. y2 is just e to the 2. So the y2 prime is easy. It's going to be e to the 2t, but we take the derivative of 2t, so it's 2e to the 2t. So when we do the Wronskian of y1, y2, the determinant, put your y1 on top, y2, your plane functions going on the top row. Put the derivatives on the second. I may not have left enough space here. E to the 2t plus 2t e to the 2t. This is 2e to the 2t. Okay, and this is going to mess up this product minus that product is the determinant. So, yep, it became fat again. So if you'll bear with me while I make my pen skinny. Okay. It's this upper left corner, t e to the 2t times the lower right counter, 2 e to the 2t, minus the lower left, e to the 2t plus 2t e to the 2t times the upper right. So let's see, this is going to be 2t, and e to the 2t times e to the 2t is e to the 4t. And when we distribute this, multiply this out, it's going to be minus e to the 4t. And then this minus times 2t times this, it's going to be minus 2t e to the 4t. So the first and the last term cancel. We're left with a negative. This all over again. I'm messing up. Minus 2. And the 2t e to the 4t and the negative 2t e to the 4t cancel. We're left with a negative e to the 4t. Now, this is never equal to 0. It can get really small. If I put like a negative number in for t, I can make it really, really, really small, but e to the 4t is never going to actually be equal to 0. So since the Wronskian is not 0, these are linearly independent. Now, with just two functions, you can lots of times just look at them and tell if they're independent or not. I'm going to write down the thing for three functions. For y1, y2, and y3, we are linearly independent. Did you do this in linear algebra? Okay. I don't. Sometimes linear algebra books cover Wronskians, and sometimes they don't. Linearly independent if, okay, in this case, the Wronskian for three functions is y1, y2, y3, and it's just the big determinant y1, y2, y3, y1 prime, y2 prime, y3 prime, and then the second derivatives. Because if you have three functions, it's a lot more difficult just to look at them and tell whether they're linearly independent. So you have to pull out something like the Wronskian. But even this can be a big mess because when you start taking derivatives going down here for first and second derivatives, if they've got products in there, then things just kind of blow up. But that's what happens for three. I don't think I'm going to give you three to do, just because it's kind of a mess. But there's one way to determine. Okay. And the whole idea behind doing this is if you have linearly independent solutions, then you can combine them to make a single general solution. So let me back up to what I was working on. Okay. Let me take a look first. Okay. So we're still working with this thing. So I backed up 2 pages. Auxiliary equation, AR squared plus BR plus C equals 0. Solutions to this auxiliary equation will generate solutions to the homogeneous form. Okay. And so what we know is that okay, this guy can have 2 real solutions. Okay, R1 and R2. And hopefully you'll be able to factor, but if not, you can always do the quadratic formula or complete the square on it. Okay. So let me, yeah. And so you can have 2 real solutions. Yeah, I'm kind of changing my order of operations here. Okay, then can we have up here equation number 2, which is covered up by this stupid sign there, it will have 2 linearly independent solutions, e to the r1t and y2 equal e to the r2t as linearly independent solutions. So there's 3 cases here, you know. If it has 2 real number solutions, then it will have linearly independent solutions, y1 equal e to the r1t, y2 equal e to the r2t, and what I said on this next one is you get the general solution by combining them in this. And I'll do some examples here. Let me get all the stuff written down here. It can also have where so the auxiliary equation can have a single repeated solution. Okay, and that's if it's a perfect square, you know, if the stuff underneath the radical is 0 in the quadratic formula. Okay, then if that's the case, 2 has y1 equals e to the rt, and y2 equals t e to the rt. then it will have e to the RT and t times e to the RT as linearly independent solutions. And this is actually in the next section, but I'm not going to prove it. I thought I'd skip some stuff. I'll just go ahead and put it all up in one place. Okay, we'll do examples of all three here in a minute. Okay. And the other possibility is that this auxiliary equation if the stuff underneath the radical in the quadratic formula is negative, it can have two complex number solutions. If we write them in a little bit different way, okay, they will be alpha plus I times beta, alpha minus I times beta, because the only thing they differ by is, think about your quadratic formula, it's that plus or minus square root thing here. And in that case, the linearly independent solutions there involve trigonometric functions, and this is something I really kind of like to do. It's just that we're behind where I want to do, so I'm just going to give you the punchline here. As y1 equal e to the alpha t cosine beta t, and y2 equal e to the alpha t sine beta t. Those as linearly independent solutions. And then look at my notes here and make sure I haven't got something. Since I'm getting out of order here, I sometimes forget something. Okay, so that's the three things here. If you have two real number solutions, then it's e to the powers. You've got one single repeated solution. That's what this is here. In other words, if that auxiliary equation is a perfect square, you'll have one single solution. And then you have e to the power and t times e to that power as linearly independent. And then if it's complex number solutions, okay, then you have to break them down into the real and the imaginary parts. The real part will be in the exponent of e, and the imaginary part will be in the argument of the trig functions. And it's really kind of neat. You start out with a differential equation that has nothing but real number coefficients. But the only way to get a solution is to actually allow yourself to work with complex numbers. And then at the end, the complex numbers all go away. So it's quite an interesting process. So we're just going to work some problems now. We've got all the important things here. So this will mostly be from 4.2, but I might pick one from 4.3 as well. This is number 6, page 160. Section. This is number 6, page 164, if I can find it. I did 161. I've already done this one. I think I did. I think I did this one yesterday. So let's scoot down and do number 17, page 164. It's not too much harder. Now we're just looking at homogeneous guys so far. So the right-hand part of the dt will be 0 as well. Okay. So we have an initial value problem. Solve the initial value problem. Y double prime minus 6y prime plus 9y equals 0. And the value of the function at 0 is 2. The value of the derivative at 0 is 25 over 3. So we're going to go through here and solve the auxiliary equation, generate the solutions for that. Then that'll give us, then we put in some constants and use the initial values over here to figure out what the constants have to be. Okay, so just to make sure we got this, okay, there's my coefficients. So the auxiliary equation is 1r squared minus 6r plus 9 equals 0. The auxiliary equation, you change your y prime to a variable and your y double prime to that square, and the y's go away. Okay. And this is nice because this guy is a perfect square. Okay, it's r minus 3 times r minus 3. So we have the second situation here. We have a repeated real number solution. Then if we back up a couple of pages to see what we're supposed to do, that means our linearly independent solutions are y1 equals e to the rt, so e to the 3t, and the other one is the same thing, except it's t times e to the rt. Not rt, it's 3t, excuse me. And these two are linearly independent because it's basically the problem example I did a while ago. Okay, and so these are linearly, can't say it, independent solutions. So our general solution is y is c1 times e to the 3t plus c2 t e to the 3t. So constant, your first function, constant times your second. Now we use these guys to figure out what C1 and C2 are. Okay. Yeah, I think the problems we're doing now are generally easier than the ones we started with. They get to be kind of long, but all you have to do to be able to solve a quadratic equation mostly. Okay, so figuring out the constants. Y of 0 equals 2. So that means if I plug a 0 in, I should get a 2. So 2 is C1 times e to the 3 times 0 plus C2 times 0 e to the 3 times 0. Everything is 0 after the plus. E to the 0 is just 1, so this is just 2. 2 equals C1. Okay. So that means then that our general solution is, so far, 2e to the 3t plus, I don't know what C2 is. We'll figure this out next. Now, to get the next part, we need to take the derivative and use this other piece of information up here. So let me go ahead and take the derivative here. Okay. The derivative of this, 2e to the 3t, let's see, 2 times e to the 3t times 3, so 6 e to the 3t. Product rule on the next one. The derivative of the first, let's see, 2 times e to the 3t. Times, that's the derivative, c2 is the derivative of the c2 times t. And then we take the first times the derivative of the second, which is e to the 3t times 3. So, I got this right? Yeah. So the derivative, 6e to the 3t plus c2e to the 3t plus c3 c2 times t e to the 3t. Okay, and somewhere along the line, I said we plug 0 into the derivative, we get a 25 over 3. So 25 over 3 is 6 times e to the 0 plus c2 times e to the 0 plus 3c2 times 0 times e to the 0 So the e's to the zeros are just 1, then there's a 0 that wipes out that last term. 25 over 3 is 6 plus c2 plus 25 minus, that's 18, so 7 over 3 is c2. Okay, so we can write our final answer down then. Y is 2e to the 3t plus 7/3. Okay, so when you've got the single repeated real number solution, you're going to get one term that's got a t in it. Now, one of the things too, we've just been working with second order linear with constant coefficients. This technique works for higher order linear constant coefficients. So let me do this is number 38. Same page, 38. And make my y triple prime minus 6y double prime minus y prime plus 6y. Let me write that better. Everything we've done with second order works for third order linear with constant coefficients. Works with fourth order, excuse me, looking for the wrong line here, linear with constant coefficients, and so on and so on. So this is, did it again, 6y, that's, just quit on ahead, minus y y prime plus 6 equals 0. So this is linear, third order linear constant coefficients. Okay. The auxiliary equation is going to be a third degree equation. R cubed minus 6r squared minus r plus 6 equals 0. The y term goes away, so to speak, and the first derivative becomes r to the first power, the second derivative r squared, the third derivative r cubed. And we solve this. By the way, you may never have seen it. There is there's a quadratic formula, there's a formula for, a general formula for solving third degree polynomials. It takes about 2/3 of a page to write down. And there is one for fourth degree polynomials too, and that takes a long time. And I have never successfully used it. I've taken a fourth degree polynomial, I knew the solution to it, and I wrote it down, tried to use the formula, and I haven't successfully used that. I bring it in one time, had an algebra professor in graduate school give those to us. I assume it's right. I don't know. Okay, and let's see, we got to, well, I can't factor everything all at once, so I'll factor the pieces. So factor r squared out of the first two, and that means I'll factor a -1 out of the second two, so they get r plus 6 both times, and r minus 6 both times. So we get 3 real number solutions, because r squared minus 1 is r plus 1, r minus 1. So the 3 unique solutions are -1, +1, and 6. And they generate solutions just like for the second degree ones, second order ones. We're going to get y1 is going to be e to the minus 1t. y2 is e to the plus 1t. And y3 is e to the 6t. The general solution is y equals c1 e to the negative t plus some constant c2 e to the positive t plus some other constant e to the 6t. So like I said, it's these if you can get these linear DEs set up, I mean, once they're set up, they're pretty fast to solve. You just have to solve quadratics or something else. Now, if this had, if one of these things is a perfect square, then we'd have, well, let me just do an example. Let's suppose we had an auxiliary equation that came out to be r minus 2 squared, r plus 3, r plus 5 squared equals 0. If we had that, we would have r equals 2, but that's repeated. R equals -3, and r equals -5, but that's repeated. What we'd get would be an e to the 2t plus t e to the 2t, because that's what happens when you have a repeated here. You'd have an e to the minus 3t, an e to the -5t plus t e to the minus 5t. So it just expands what we're doing already. You know, of course, if we had a DE, I don't really want to write down what the differential equation, that'd be a fifth order differential equation that goes with that. But that's just how the auxiliary solutions are going to generate linearly independent solutions. And as long as I'm doing this, just kind of going off on a tangent here. Here we have r minus 1 cubed equals 0. So this would come from a third order DE, and you would have one solution, but it actually shows up 3 times. So what you would get for that is e to the 1t, t e to the 1t, and t squared e to the 1t. But again, I'm getting kind of ahead of myself, but I'm hoping you kind of see a pattern here on these things. And if you had r minus 1 to the 4th, we'd have another term. It'd be t to the cubed, e to the t. Okay, so I want to do one complex number one, and then we'll leave, and I will come in with an assignment on Thursday so that I can get a little bit more caught up here and just kind of mix them all up. The book breaks things up into 2 sections, and I don't think that needs to happen. But here's one from the next section, page 1, something or other. 1, where'd it go? Number 6, 172. Find a general solution. Y double prime minus 4y prime plus 7y equals 0. So this is not an initial value problem. Our final answer is going to have a couple of constants in there. The auxiliary equation, well, A is 1, B is negative 4, and C is 7. It's going to be r squared minus 4r plus 7 equals 0. And I'm going to solve this by completing the square. Okay, so completing the square, subtract 7. Okay, the left-hand side, take half. You can use quadratic formula. I just feel like completing the square today. Take half of the first degree coefficient, square that, add it to both sides. So on the left, we have r minus 2 squared. On the right, we had a negative 7, and 4 is a negative 3. So take the square roots. R minus 2 be plus or minus the square root of negative 3. And remember, this is going to be square root of the negative part is I. So plus or minus I square root of 3. So when you add 2 to both sides, and we like to write the I in front of the radical, otherwise it almost kind of gets underneath it. Okay, so what we're looking at here, then, remember the way I wrote this down. This is alpha plus I beta, or beta I, alpha minus I beta. And the solutions are y1 equals e to the alpha t, so e to the 2t, times the cosine of beta t, okay. And y2 is the same thing except sine. And what you really need to show, and which the Wronskian shows real well, is that things like this are linearly independent. Okay. And that's not the general solution. The general solution is to slap a couple of constants in front of them. C1 e to the 2t cosine square root of 3t plus C2 e to the 2t sine the square root of 3. And what this looks like, it's just, if you graph this, it's going to blow up real fast, but it looks, because you have an exponential function going up, so it looks like that. Okay, so we'll make an assignment next time. Were there any questions, any more questions about this project? I've answered a few. Were you able to do the number 1, the very first thing? It's a mess no matter how you look at it. But, well, well, you don't have to work number 1 to be able to do the rest of it. Let's say that. So I've got it set up that even if you couldn't make to get through all of that, you can still use the result. Any other questions about those things? If you need what you can always do is I can perhaps print out what you got on your calculator, or you could, if you wanted to, take a picture on your phone. Of course, you've got to get it from your phone to somewhere, but I've had people, I'm talking now to Renee, who's off campus. She could take a picture on her phone if it's of her calculator and send it to me. People have sent me pictures of it. Okay, but if you got that, I'll take it. If you've still got a little more to do on that, I'll take it later too, because I've got to catch up